Hey, what up, guys? So let's do chapter four. I guess we're kind of shifting from this static kind of architecture of linear spaces now to dynamic transformations that act upon them. This transformations and observables. These are linear algebraic arguments, right? Has nothing yet to do with any like quantum physics or all this stuff, but this is inherently a linear. A kind of vector argument, right? So these are agents of change and observation. So the central equation of this chapter, a times x equals lambda times x, is this primary kind of instrument for decrypting the intrinsic properties of a system. So this reveals stable states, or the eigenvectors, that remain unchanged in direction under transformation, and the scaling factors, the eigenvalues, that quantify the effect of this transformation on these states. And so the master key equation, the master key to analyzing this system dynamics is this guy. So we basically decrypt the system states by means of this kind of eigen decomposition. So a linear form. Let's start about this, right? A linear form is a measurement device. It is a linear function L that maps a vector from the space V to a single scalar in the underlying field K. And this linearity is defined by two properties. So it distributes over vector addition and commutes with scalar multiplication, as with a lot of our number fields. And in the n-dimensional real space, any linear form is equivalent to the dot product with a fixed vector L. And its coefficients, or the coefficients of L, can then be seen as parameters of the hyperplane, defining a specific measurement orientation. So a way to think about this is it's a space of continuous functions, or an integral against a kernel function L of t that acts as a linear form. And so this is an abstractified way that kind of produces a weighted average. And so the second kind of linear form in complex space introduces antilinearity, where the form of a scaled vector is the complex conjugate of the scalar times the form of the vector. I mean, if you want a background on this, I'm going to actually, I'm making a series in parallel on complex analysis, which is going to get into this a little bit, and abstractify this slightly. But the structure of this structure is fundamental to the inner products used in quantum mechanics. So for any choice of basis in the vector space V, a linear form L is completely determined by the n-scalar values L sub k obtained by applying the form to each basis vector. And then hence the action of the form on any vector is simply the sum of these coefficients multiplied by the vector's components. So in essence, a linear form reads the coordinates of a vector and reports a single synthesized value. So where a linear form maps a vector to a scalar, a linear operator then maps a vector space to another vector space, preserving the underlying linear structure. And so an operator A from space V to space W is linear if it distributes over addition and commutes with scalar multiplication. So I don't know how many people have really read through Shilov's linear algebra before, but this is, still kind of elementary. And basically, this is the foundation of quantum mechanics that, if you take a normal linear algebra class in college, you're not going to experience this whatsoever. But this is really, really illuminating. So once we fix a basis for the input space V and the output space W, any linear operator can be uniquely represented as a matrix. And so the columns of this matrix are coordinate vectors of the images of the input basis vectors. And so the jth column of this matrix A consists of coefficients A, I, J that express the transform basis vector A, E, J in terms of this output basis vectors Fi. I hope that's kind of clear. If not, I would go through the text and read it because it'll explain it way better than I do. But this matrix, right, from a high level, it's a representation that provides a concrete computational engine, right? So the transformation of an abstract vector x onto vector y is achieved by multiplying the coordinate vector xi by the matrix A to obtain the output coordinate vector eta. So examples range from the zero operator, which it basically just collapses all vectors into the origin. Of course, we always have to have that. And then also we have to have an identity operator, which leaves all vectors unchanged to geometric transformations like rotations and such. So which is going to be very critical. But the crucial point, right, is this one-to-one correspondence between operators and matrices once a coordinate system is chosen. So once you choose a coordinate system, there's a one-to-one correspondence between the operators and the matrices between them. So the set of all linear operators then between two spaces forms a vector space in its own right. So we can then define the sum of two operators, A and B, as the operator that produces the sum of their individual outputs, and then we can scale the operator by a scalar lambda. And most importantly, we can define the product or composition of two operators. And then the product A through B or AB represents the sequential application of operator B followed by operator A. And this algebra then of operators obeys standard properties like associativity and distributivity, but it includes a critical feature of complex systems, non-commutativity. In general, and this is going to generalize to many fields in mathematics and physics and finance and machine learning and whatever the heck field you are in general, right, the operator AB is not the same as BA in this kind of context, right? The order of operations matters. And this is consequential because the provided example here of two simple matrices A, B's illustrates this profoundly or pointedly, that AB produces a non-zero result while BA produces the zero matrix. So this non-commutation is not kind of some mathematical quirk or kink. It's actually a reflection of the real world phenomena where sequential actions have then path-dependent outcomes. Sorry, not incomes. I don't know what I was trying to say. But hence, the algebraic structure of operators, right, corresponds precisely to an algebra of matrices. So the sum of two operators corresponds to the element-wise sum of their matrices, and hence scalar multiplication of an operator corresponds to the element-wise scalar multiplication of its matrix. And then the composition of two operators corresponds to the matrix product defined by the familiar row-column multiplication rule. And then this rule, where the kjth element, sorry, I missaw that, of the product AB is the sum over I of AKI times BIJ, and that's precisely what's required to correctly track the transformation of the basis vectors. So we can then build the matrices from elementary units, such as the matrix ERS, where one in the RS position, this has one in the SRS, in the RS position, and zeros everywhere else. And so this can then be used to perform specific row and column operations. And for larger kind of structured systems, block multiplication provides this powerful simplification that allows partitioned matrices to be multiplied as if their blocks were scalar elements, provided that the partitioning is compatible. So the transpose of a matrix, A transpose, is formed by interchanging the rows and columns. And so a key property is that the transpose of the product is the product of the transpose in reverse order. And this is this fundamental reversal is kind of a structural property. So the Binet-Cauchy formula provides this connection between the geometry of a product transformation and the geometry of the individual transformations. So it states that any k by k minor, so for any k by k minor, let's see, am I on the right spot? Yes, I am. Any k by k minor of the product matrix AB can be calculated as the sum of over all k by k minors of A and B, and the direct corollary is the rank inequality. And so the rank of a product of matrices cannot exceed the minimum of their individual ranks. This is this information kind of theoretical principle. So a sequence then of transformations, as we're seeing here, cannot generate more linearly independent outputs than the most restrictive transformation in the sequence. So for quasi-diagonal or block diagonal matrices, as shown here, the structure simplifies dramatically. So the product of two block diagonal matrices is a block diagonal matrix where the corresponding blocks are simply multiplied. And so this reflects kind of this decoupling of the operator's action on specific independent subspaces. So let's put our attention more to the range and null space. So with every linear operator A, we associate two fundamental subspaces. The range, or image, in other words, is the set of all possible output vectors. Sorry, I need a drink. My throat is really dry. But it is a subspace of the codomain W. In the null space, or kernel, is the set of all input vectors in the domain V that are mapped to zero vector, and it is a subspace of V. So these two subspaces quantify the operator's effect on the space, and the rank nullity theorem states that a conservation law, right? The dimension of the range plus the dimension of the null space is equal to the dimension of the codomain. Oh, sorry, dimension of the domain. Sorry, not codomain. Sorry, I'm in a topology brain for a second. In terms of matrices, the dimension of the range is the rank of the matrix. So the dimension of the null space is therefore n minus the rank. This relationship then will govern the existence, right? The existence of inverses. And so we've talked a little bit, I told you to look up a formula for inverse, or you could just look at it in Shilov's text as he kind of introduces it his way. But now we're really talking about existence of inverses, and we have to find this only through the kind of eigen decomposition that we're leading to. But a left inverse exists if and only if the null space is trivial, meaning that the operator is injective and no information is lost. And the right inverse exists if and only if the range is the entire codomain, meaning the operator is surjective and can reach any state in the target space. Please let me know if you have any questions on that. I hope that was clear. But when an operator maps a space to itself, right, is as common as this study in the study of dynamical systems. The set of all such operators, where an operator maps a space to itself, forms this kind of rich structure known as an algebra. So it's a rich algebraic structure which we can know as, or we can call it algebra. It forms an algebra. So the key property then of these operators is that the determinant of a product is the determinant of the matrix. The determinant of the product is the product of the determinants. We call this officially an algebra. So this means basically, I want you to think about it like this, that the volume scaling factor of a composite transformation is the product of the individual scaling factors. So an operator A, in other words, has an inverse if and only if the determinant is non-zero. And then the matrix of the inverse operator can be constructed explicitly using the cofactor matrix, where the ijth element of A inverse is the jith element of the cofactor matrix, scaled by the reciprocal of the determinant. And as this formula kind of provides an explicit means to reverse a state transformation by an operational logic or algebra, basically. So in a invariant subspace, let's talk about this now, this definition. So an invariant subspace is a region of the state space which is mapped onto itself by an operator. And if a subspace U is invariant under the operator A for any vector in U, the transformed vector then would be AX, or AX will also be in U. So the dynamics then are self-contained within U. And if we choose a basis for the whole space that is adapted to this subspace, the matrix representation of the operator takes on an upper block, upper triangular form, as shown here. And then the block A11 describes this operator's action on the invariant subspace U, decoupled from the rest of the space in one direction. And so if the entire space is decomposed into a direct sum of invariant subspaces, the matrix becomes block diagonal, completely separating the system's dynamics into an independent lower dimensional component. And then by finding these invariant subspaces, this would be a strategy then by finding them, to reduce the complexity of a system. The ultimate decomposition, then, of an operator's action is achieved by finding, drum roll, its eigenvectors, right? So an eigenvector, really the most intuitive way to think about this, and it's kind of paradoxical because the most intuitive way to think about it is from a rigorous mathematical standpoint, the eigenvector and the eigenvalues. You hear these words thrown around, and we have somewhat of a vague idea of what they are, but an eigenvector is a non-zero vector x such that its transformation ax is simply the scalar multiple of itself, lambda x. Just as we were kind of defining these spaces that have these properties that are kind of like Russian nesting dolls within themselves, right? So the vector's direction itself is invariant under the transformation, and hence the scalar lambda, the corresponding eigenvalue of lambda, it quantifies the stretching and shrinking along that invariant direction. And so eigenvalues then are found as the roots of the characteristic equation, which sets the determinant of the matrix A minus lambda equals to the identity to 0, this famous expression we all know. And an operator on the n-dimensional space is diagonalizable if it possesses linearly dependent eigenvectors. In this case, the operator's matrix can be transformed into a single diagonal matrix whose entries are the eigenvalues, and in this diagonal form, capital lambda, this capital lambda is achieved by a change of basis to the eigenvectors captured in the matrix M, the matrix V. So not all operators are diagonalizable. So a shear transformation, for example, has fewer independent eigenvectors than the dimension of the space, indicating a more complex, non-decomposable dynamic. So this kind of mathematical framework of operators and their eigenvalues finds its primary application in physics. So, of course, quantum mechanics, physical observables like energy, momentum, and spin are all represented by linear operators. So the measurement of an observable on a system in a state psi yields a definite value lambda if and only if psi is an eigenvector of the corresponding operator A, the operator A, with eigenvalue lambda. So then the time-independent Schrodinger equation here, as we show, which we'll discuss a little bit more in another book, but it's this itself is kind of an eigenvalue equation for the Hamiltonian operator H hat, where its eigenvalues are allowed quantized energy levels of the system. And in classical mechanics, the analysis of coupled oscillations, which we will also cover, leads to the generalized eigenvalue problem, where the eigenvalues correspond to the squares, the natural frequencies of vibration, and the eigenvectors describe the shapes of these normal modes. So this kind of principle here is unifying, right? The technique of eigenanalysis provides the fundamental method for decoding the intrinsic dynamics and measurable properties of systems across all domains of science and engineering. So let's work through some problems. So problem 1 requires of us to construct the dual space of linear forms and finding its dimension. So the set of linear forms on the space K itself forms a linear space. So let's formulate the strategy, right? So if K has basis E1 through En, we can define the corresponding dual basis in K star, where the jth dual basis vector JL is defined by its action on the original basis Lj of Ek is 1 if J equals K and 0 otherwise. So this dual basis has n elements, and the dimension of the dual space K star is also an n. So problem 2 asks to identify which functions are linear operators. So I guess the most straightforward way you could approach this is really just looking at the definition, right? So linearity requires that the operator maps to the zero vector, and the zero vector that it scales linearly. So the functions in A and B are affine translations and not linear, and the function in D is nonlinear due to the multiplication by x. And so the function in F then let's look over here. the function in f basically involves this non-linear trigonometric function. So the functions e and c, e and g satisfy the definition of linearity, and then problem 3 over here tells us it asks if multiplication by t squared, and differentiation under linear operators on the space of polynomials. And then all three are indeed, they have to be linear because they distribute over addition and commute with scalar multiplication, as we defined earlier. So problem 4 provides the action of an operator A on a specific basis of vectors v1, x2, x3, and we're asked to find the matrix of A in two different bases. So first is the standard basis vectors, Pj, and to do this, we must express Pj as a linear combination of xk's, and then use basically this kind of idea that we were talking about, but then use the linearity of A to find its action on the Pj's, and so this resulting vector can be expressed in the standard basis and form the columns of the desired matrix. And then second, the basis of the xj vectors themselves. And so in this case, the columns of the matrix simply the coordinate representations of the output vectors ak or axk, represented by this standard basis as given in the problem statement. So problem 5 here, what this kind of represents, or what this is trying to examine, is the algebra of rotation operators in 3 dimensions. So we're given the matrices for 90 degrees rotations in the x, y, z axes here, which would look like that. And then a direct matrix multiplication just confirms that the fourth power of each is the identity, as 490 degree rotations is a complete circle. And so it also confirms that the product AB is not equal to BA, demonstrating that rotations in 3 dimensions is non-commutative. So the squares of the matrices then would represent 180 degree rotations, do commute though. So finally, the product AB is shown not to be equal to AB squared, highlighting the consequences of course, as we mentioned, non-commutativity. Let's work on problems 6, 7, and 10. So 6 considers 2 operators in the space of polynomials. A is differentiation, B is multiplication by t. We find that their product is non-commutative. Okay, so to do that, the operator AB acts on polynomial P by first multiplying it by t, then differentiating. So which by the product rule yields P plus t times P prime. And then the operator AB first differentiates P, then multiplies by t, yielding t times P prime. The difference then is AB minus BA. And this operator that returns the original polynomial P is the identity operator. And this commuter relation then AB minus BA equals I is a foundational kind of structure. Of course, that's hinting at quantum mechanics. So problem 7 asks about binomial formulas. So the familiar formula, like a plus b squared equals b squared plus 2ab plus b squared, holds if and only if b commute. So if they do not, as we've shown here by just expanding it out, if they do not, we must retain these distinct terms AB and BA in their correct order. And the expansion of A plus B cubed, for example, would involve 8 possible 3-letter products of A and B. So that's kind of how we do this. But for problem 10, we would require computing the product of 2 specific 3x3 matrices. So both matrices are rank 1. Their product then is through direct row by column multiplication, and this results in the 0 matrix. So this illustrates that the product of 2, non-zero matrices can be 0, which highlights the key difference in scalar arithmetic. Problem 11 asks for the n power of 2 matrices. So the first matrix, a shear transformation in some way, can be powered by induction. So a to the k times a shows that the top right entry simply increments here. So a to the k times k, you can show this here. And sorry, I keep forgetting to change the slide. Please forgive me. But yeah, it just kind of shows that a to the n has that in or has in that position, and then the second matrix is a rotation by an angle theta. So raising it to the nth power corresponds to performing a rotation n times, and then this results in a rotation by n theta. So problem 12 here asks to find all 2 by 2 real matrices whose square is the zero matrix. So to do this, we set the resulting matrix equal to 0, and then derive a system of equations for the 4 entries. The condition simplifies to the trace, a plus d being 0, and the determinant AD minus BC being 0, and then this implies that D equals negative A, and A squared plus BC also equals 0, and any matrix satisfying these 2 conditions has a solution. So that's kind of how we find that constraint. Problem 15 asks to prove the relation AB minus BA equals I is impossible for operators on finite dimensional space. So this is kind of a necessity for the Hilbert spaces, which are going to come later, but this is proven by just using the trace function. So the trace of a commutator, the trace of AB minus BA, that's the commutator, it's always 0. So however, the trace of the identity matrix is the dimension of the space, which is non-zero, and this contradiction proves that this is impossible. So 21 asks for the inverse of 2 matrices. The upper triangular matrix can be inverted systematically using the Gauss-Jordan elimination method. So we can do that as so. That's the first thing that I just said. And then the second matrix B is called the Hadamard matrix. And one can define or verify that the columns are orthogonal. So for an orthogonal matrix, its inverse is equal to this transpose, scaled by the square length of its column vectors. So here B inverse is equal to B transpose, which is simply B itself. 25 considers operators on the finite dimensional space of polynomials. So operator A removes a constant term and divides by t. Hold on, I need a drink. Oh, my throat's dry. The operator B multiplies by t. And then the composition AB is the identity operator. However, BA is not, as it annihilates with a constant term. So because A is not injective, it maps all constant polynomials to the zero polynomial, and it has a non-trivial kernel, and therefore it cannot have a true two-sided inverse. Problem 26 follows up by just showing that the operator B has infinitely many left inverses. So a left inverse C must satisfy CB equals I. So the operator C can be defined to perform the action of A, but it has a freedom in how it maps the constant term of its input polynomial, leading to an infinite family of possible left inverses. Problem 35 requires finding the eigenvalues and eigenvectors for 2 matrices. So for a matrix A, this is a solution, we solve the characteristic equation and find this 3 distinct real eigenvectors, or eigenvalues, sorry, 2, 1, and negative 1. For each eigenvalue, we solve the corresponding homogeneous system. So A minus lambda I equals times x equals 0 to find the associated eigenvector. And so for matrix C, the characteristic equation yields the single eigenvector or eigenvalue. Sorry, I keep saying value and vector switch, but eigenvalue lambda equals 2 with an algebraic multiplicity of 3. However, when we solve for the eigenvectors, we find that the null space of C minus 2i is only one-dimensional. So the matrix has only one independent eigenvector, and therefore it is not diagonalizable. Problem 38 tells us that, and it asks for all invariant subspaces of diagonal operator with distinct eigenvalues. So at first this might seem like kind of a challenging problem, which it is, but because it's asking you to abstract, define, generalize this, right? This is kind of a level of thinking that I really like from these problems. So the eigenvectors e1 through en form a basis. So we construct this, and then given these definitions, any subspace spanned by a subset of these basis eigenvectors is an invariant subspace. And since there are 2 to the n possible subsets of the n basis vectors, there are 2 to the n invariant subspaces in total, ranging from the 0 subspace to the entire space V. Thank you for watching, and I hope you guys are enjoying this, and I'll see you guys next time. Bye-bye.